a consistent and comprehensive model which can contain observational diagnostics. And of course, we want to understand why this structure dynamics is like it is. So this conference is called New Trends. So what is new in these things? For one, I will show you some results concerning the dynamics and small-scale structure, and maybe something that's more new or newer is the modeling of non-equilibrium processes in the framework of these simulations. And I will show you two examples. There's a chemistry simulation for carbon monoxide, and also some new results which I will briefly address for hydrogen ionization. So let me give you first an introduction. So when we talk about small scales, so what do we really mean? And I have this really nice movie here from Mats Karlsson. So we'll zoom in from the full disk of the sun to the really small granular scales, that you really get an impression on what tiny details of the solar atmosphere we're really interested in. You see this well-known granulation pattern with a spatial scale of roughly, say, order of 1,000 kilometers. So we want to look at the chromosphere. So this is a picture from calcium 2H line in the line core, which shows the chromosphere, or maybe not. That's not so sure. And you see distinct regions. Of course, these brighter features here are related to magnetic fields, which you address, which you call the magnetic network. And these darker regions here, that's what I'm interested in. Those are these inter-network regions. And this is a picture taken in the H-alpha core, and you see a really vast structure here, really complicated looking. And essentially, you have apparently magnetic fields everywhere, giving it this really interesting look. So I'm interested in the internetwork. That's what I'm going to focus on. And so the question is, why should we be interested in working on the chromosphere? And just give you some open questions that make this layer really interesting. So first of all, it's still not really clear if you have it, how structured and how dynamic it is. There's this really classical picture that we have a homogeneous, well-stratified layer, or what more recent works show that you have something really intermittent, some rapidly evolving, some really inhomogeneous. And if you have this latter case, so the question is, what causes these inhomogeneities? Maybe carbon monoxide is a cooling agent. That's one of the questions. And also the magnetic field on these scales is, there are still many open questions, and especially the influence on wave propagation, and for example on molecular diagnostics, like this for solar physics well-used G-band diagnostic. And one of the central questions is actually the heating of the chromosphere. Is it done by acoustic waves or MHD processes? And this, of course, also has important implications not for the sun only, but also for other stellar chromospheres. So we heard about the code called cobalt before today. So this is just some nice view graph to summarize a little bit what cobalt can do. So you see on one side these more local convection simulations, and also what Bernd Partner is doing mostly, these star-in-a-box models, and different star types can be addressed from the sun, A stars or giants, whatsoever. And those are some newer, interesting extensions of the code. Some recent upgrades. For one, we have time-dependent chemistry, which was used so far for carbon monoxide in the solar atmosphere, but in principle can be used for a broad range of other applications. Then we have the extension to magnetohydrodynamics, where we have first models, but still working on that. And finally, this is under construction still, the time-dependent hydrogen ionization, which I will show some results, but with the caveat that there's still some work to be done. coupling on the question state has still to be done. So, but let's start with something really simple. So, some hydrodynamic model. And you can see here, it's a bit distorted I think, but well. This is a small portion of the solar surface layers, roughly covering a few granules in horizontal extent, and it goes down in the upper convection zone, of course, to drive the whole simulation. And you will see this better in a moment, includes the photosphere and the low to middle chromosphere. So this movie shows a vertical cross-section through this model, and color-coded here is the gas temperature. So the red color means high temperature, goes to 16,000 kelvins, and black is really cold, with down to 2,000 Kelvin. And you can see here the convection zone. You really clearly see thermal convection with plumes falling down here. You see the photosphere, which is relatively, well, has a little structure apparently in this picture, and a really vast action going on in the chromosphere, where you have a lot of propagating shock waves. So if we now cut through this model horizontally in the chromosphere, what you see is this. So this is again the temperature, and you see really bright features here, which are about 7,000 Kelvin, which are hot shock fronts. And in between you see really cool bubbles with temperatures down to 2,000 Kelvin only, which are also caused by these propagating shock waves. And these cool temperatures are caused by the adiabatic expansion of these regions once these shock waves pass through. So you can actually see sometimes some bright spots, which then evolve into a ring. That is just because this shock wave that comes from below this plane that we are seeing here just cut through this viewing layer. So this is really a typical outcome of these simulations. It's really fast evolving. So one step further is now the inclusion of magnetic field. And this model is somewhat similar, a little bit smaller than the one before, but includes now a magnetic field, and it's quite a weak magnetic field. The initial field was 10 Gauss only, and it was a vertical unipolar field, so really simple configuration. And again, you see here the thermal structure of the model is very similar to the one before. And here you see now the magnetic field. So there's a flux tube that you can see, but we will go for a similar movie here. So instead of the gas temperature, I'm now showing the logarithmic magnetic field strength. And you've seen the very blue screen was the initial model, so really homogeneous magnetic field. And now you see how slowly some magnetic field is advected with the hydrodynamic flows, and is concentrated in the intergranular lanes and forming some flux tubes which swim somehow like corks in the uppermost convection zone layer. And but what you hopefully can also see from behind is that you have really fast-moving features in the very uppermost layers, and which is really different from the motions below. So this black line here is plasma beta equal 1, and this has some interesting function apparently, because it somehow separates these lower layers, where you have really smooth, slow dynamics, from a very rapidly evolving upper part. So now again you see horizontal cross sections in magnetic field strength, logarithm of it, but at different heights. So here it's really deep down in the convection zone, here at the bottom of the photosphere, and here up in the chromosphere. And Those who are familiar with solar physics maybe at least will recognize this a little bit, where you have these really confined structures which are flux tubes and some field concentrations in the lanes between. So there you have a really high degree of structuredness. And very in contrast, in the chromosphere you see a much smoother distribution apparently, which nevertheless is fluctuating quite a lot, and you see a lot of fast-moving features there. So it's certainly very different from what you see in the layers below. So just let me summarize this before we go to this other part of the talk. So these model chromosphere, which I use here for the, as basis for the other ingredients I will show, are characterized by shock fronts and really cool intermediate regions, and these are a direct result of shock waves. And also this magnetic field in the chromosphere is very dynamic. And you see this surface of plasma beta equal 1 separated somehow these domains. And what gives rise, what means if you have these really fast evolving structures there, you can expect some deviations from equilibrium conditions, because everything is changing so fast. One has to ask themselves, do these methods that we usually apply still hold in this case? And what is also very important for these models is to ask, are the temperature amplitudes correct? Because the radiative transfer that is used here is quite simplified, so it's still gray in LTE, so this is maybe the simplest case you can think of, and this needs definitely to be improved. It means some non-equilibrium effects have to be taken into account. And the question is, which are most important? And of course, you have to improve these simulations and then to check it with observations then, to see what's really necessary. Okay, so one first idea was that carbon monoxide might play an important role in structuring the atmosphere. So what we did was...
Did you do DNA?
I have to wait a bit longer for this.
Yeah, right.
And to include the time-dependent treatment of a chemical reaction network and the affection and the radiative cooling due to CO into the code. And this reaction network essentially consists of 7 chemical species, which are important for the formation of carbon monoxide. You can see in this scheme here, you have carbon monoxide here, and here are some reaction channels which connect carbon monoxide with other species like CH or carbon or OH and so on. So you construct a set of the most important species and reaction channels. These are just the data that come out that you need to do that. And then what you get really is a system of rate equations. And that, of course, you can solve. And this gives you then the CO number density and also the number densities for every other species included for every spatial position and every time in the simulation. And this is what comes out for carbon monoxide. So this is again a vertical cross-section. And color-coded now is the absolute CO number density. So you have to keep in mind there is some density certification in the atmosphere. And what you see here is that the highest amount of carbon monoxide apparently is found in cool regions in the middle photosphere. So, well, yeah, density is decreasing quite a lot in the atmosphere, and to see the relative contribution of CO, it's better to plot the CO abundance, which gives this picture here. And you see carbon monoxide is quite abundant throughout the whole chromosphere, which means this red color. It's almost not abundant in the convection zone because the temperatures are quite too high there. But what you can see is there are some places where you have less carbon monoxide within these isocontours, which actually display moving shock waves. I see it better in this plot even, where you have now the fraction of all carbon atoms bound in CO and the total number available. So means in all species that contain carbon, and this fraction only gives you what is in carbon monoxide. And if you plot this again, you see this. Of course, there is nothing really down here because it's too hot. You have values up to 1. That means that every carbon atom that's available is bound in carbon monoxide. So it's really aggressive formation of carbon monoxide. But you see these interesting things here in these hot shock waves. There you see some kind of gradual dissociation here. So it's very abundant here, and there it's gone. And this is simply explained as the shock waves moves into a carbon monoxide-rich medium, and it takes some time before all carbon monoxide atoms are destroyed. So you have some finite timescales on which this is happening. So apparently, at least the message we can get from here is it is apparently important to do a time-dependent treatment of carbon monoxide in the upper layers. And here you see these pictures again, but as a time series now. So this is the absolute amount again, and this is now this logarithmic absolute number density, so you can see better. So the density effect is removed, and you see these shock waves come through and destroy carbon monoxide, but it's quickly formed after these shock waves went through. Okay, then if you go then to 3D simulations, you can make these nice kind of plots where you have now isosurfaces here. This blue isosurfaces for carbon monoxide means you somehow have some CO clouds in the middle, photosphere sitting here, and inside the cool regions of the reverse granulation pattern. Okay, next step is then radiative cooling of these CO lines, which was thought to be important for the atmosphere. And how did we do this? So we have two opacity bands. First is the continuum band, as usual, with Rosland mean opacity. And but the second one now takes into account the additional CO line opacity in the first fundamental band, about 4.7 micrometers. And this second opacity band is calculated from this CO number density that comes out of the simulation. That means this band is changing. It depends on where you are on the simulation and what time you're looking at. And of course, then you just solve the radiative transfer equation again. And this enters then the energy equation as net radiative heating rate. And this quantity is shown here in vertical cross sections. So this means this quantity is the change of the internal energy of the gas due to the radiation field. And here you see it for the continuum, and here only for the contribution of carbon monoxide. And where here dark colors, so black and dark red, means you have radiative heating, so there's some absorption. And the bright colors, like here, means there's radiative cooling, so emission of radiation. And you see different regions here in these plots. For example, the most obvious maybe is this one here at the bottom of the photosphere, which of course defines the photosphere in some way, where you have a strong emission of radiation. But you find that also in these really hot shock waves, you find some significant emission of radiation. But on the other hand, you find also some regions here where you have some net heating due to the surrounding hot gas. So this is for the continuum. I think this can be well understood. And for carbon monoxide, you find something similar. So in the very shock front, where you still have some significant amount of CO left, you find some emission of radiation, but you also find in these cool pockets in between, where you have a strong amount of CO, you find some additional heating due to CO. So both effects are found there. But the actual is here, and I don't go into too much detail, that even this can't change the thermal structure. And so the question is, why is that? So it can't do, and so why is that? And a really easy answer is that the timescales that are needed for CO to cool the gas radiatively is much longer than the dynamical timescales that you find in the atmosphere. That means if you have some cool pocket like this here, and this starts to cool down this gas, it takes not long before another shockwave just comes and passes through and destroys all CO. And the whole process has to start again. And the time in between is just not enough to really make a significant effect for the cooling. So this is the conclusion for the carbon monoxide. And so the average temperature is about only 100 Kelvin change. And these long proposed thermal bifurcation of the solar atmosphere due to CO is thus not taking place. And but nevertheless, you find CO is there, and it's really dynamical and confined to some regions in the atmosphere that could serve at least as diagnostic, maybe. But the good news is maybe here that you don't have to include it in your simulations, so it saves some work. A few comments to hydrogen ionization, which is more or less only a multi-D follow-up of the work by Bob and Mats. So we use the same recipe by my master student, Solom, developed in Oslo, which uses a model atom of hydrogen with 5 bound energy levels and the ionized stage. And again, we get a rate equation system which we can solve, and this gives us the level populations and with that the electron density for all spatial positions and time steps. And you will hear more about this in the next talk. But just let me show these few view graphs here. So again, you see vertical cross sections for the simulation box. On the left hand, let's start here. So this is the gas temperature again. You see here the bottom of the photosphere where you have high temperatures, and you can see some faint shockwave structures here. And these are the conventional LTE simulations, where you have the LTE electron density, so this is really coupled to the local gas temperature, and the ionization degree of hydrogen. So what you see there is that it really depends on the local gas temperature. So when you have a shock wave here, so hot temperatures, you find a high ionization degree here, and with that also a high electron density. But if you now do this non-LTE treatment, you find this. It means this is really smooth, and the tight correlation to the gas temperature is apparently lost. So why is that? I think Bob already said this in a comment earlier. This is because the recombination rates are much longer than the dynamical timescales again. So it really takes too long, and essentially the shock waves setting a more or less constant level of ionization in the upper atmosphere. But this shows us that the deviation from equilibrium definitely has to be taken into account. And the next step, of course, would be here to make a back coupling to the internal energy of the gas. This has still to be done for cobalt. So, I'm coming to the last part. comparison with observations. So when you do simulations, then you always have to ask yourself, how realistic are those simulations? And how can you check this? Then, of course, what you're interested in is to do really detailed comparison with observations, to see if they can reproduce the observables or not, and to find out if there's something missing, maybe in your simulation. The problem for the solar chrometry is that you only have a few diagnostics available. For example, really famous ones are the calcium to H and K line. But there you need really narrow filters to really observe the chromosphere, because as soon as you have some contributions from the line rings, you're looking essentially at deeper layers. That means into the photosphere. And there's some extended formation height ranges, so those are really complicated or some troublesome. And also you need non-equilibrium effects here for interpretation, and also for calculating synthetic intensity images from your simulations. This is really troublesome. Much better situation you find for the sub or millimeter wavelengths. There you have quite an easy situation. So it's more or less due to thermal free opacity, and for the source function at least LTE is valid. That makes it much easier. That means that the local gas temperature more or less contributes linearly to the emergent continuum intensity. And then, of course, you can much easier interpret the observations. Problem so far was that you don't have observations with high enough spatial resolution to really exploit this diagnostic. So what's coming up quite soon, hopefully, is ALMA, which will be built, is currently built in the Chilean Andes, and will start in, I think, 2012 will be the full scientific operation. And it will consist of 50 antennae with diameters of 12 meters, and has wavelengths down to 0.3 in the final stage until 3.6 millimeters, and has a large number of spectral channels which it can observe at the same time within a certain wavelength band, and can switch even between the different bands in almost no time, and gives you even polarization signal. So this is a really unique tool one should look for. So, but what can we expect to see with this kind of instrument? And for that we took these models I showed here, historical models, and plug it into some intensity synthesis code. Here we used LintRAW 3D and also the RH code from Vitamog. And what you get in the end is then a data set of synthetic continuum intensity maps as a function of time, as a function of wavelength, and inclination angle, so position on the solar disk. We did this for some wavelengths that are interesting for ALMA, and for positions on the disk going from center of disk towards the limb, or close to the limb. But that's always an important test for a model. And so here you see gas temperature and emergent intensity next to each other. You can guess what is what, and you see hardly a difference, which is, I think, a really good sign. You have find the same spatial scales here, and also the time scales are the same, so this looks almost like a one-to-one mapping. And if you look at different wavelengths, here's the shortest, towards the longest wavelength, you see some differences in pattern. And these differences are simply due to the fact that that the different wavelengths have different formation heights in the atmosphere. So it's looking at different layers there. Okay, so here now the non-equilibrium effect come into play. You saw I had these non-LTE electron densities coming out of the code. And if you now use those for the intensity synthesis, then you also find an effect for the optical depth here. So in the left panel, you see again in the vertical cross section the contribution to the intensity. That means for a position here, the intensity contribution along vertical column it comes from this layer more or less. And there you look into some cool region, then it comes from down here. And here you maybe have some shock wave again closer to the upper boundary, then you look, your intensity comes from here. So there's a large variation in the formation height due to a large fluctuation in electron density. And if you now use these non-LTE electron densities, which were much, much smoother, then you, as expected, find these contributions here, which are, well, they still fluctuate, but they are more or less from a smaller height range, which of course is really nice for the interpretation, because then you're looking at not unknown corrugated surfaces, but more or less at the same layer really. And one of my last slides here is the formation height for the shortest wavelengths. So this here is down here is the middle photosphere, and this is maybe the what is the bottom of the chromosphere, and you find for the short wavelength quite a peak at the very low chromosphere. That is this with non-equilibrium thing, and if you go to the longer wavelength, you will see that it moves to higher layers, which is a really nice effect, because this way you can actually scan through the atmosphere by just looking at different wavelengths. And this is now a sequence with different position on the disk. You start here at disk center now, and then you go out towards the limb, and then you see how the intensity changes. And actually, when you look at the limb, you look front on the surface, and towards the limb you look more from the side, so you might even get some idea about the 3D structure of the atmosphere. So the conclusion here is that you have a really nice mapping of the thermal structure at these wavelengths, and together with these different formation heights, which depend then on wavelength and the inclination angle, you might even construct something like a tomography, which gives you really the 3D structure of the atmosphere, and which looks really promising. And you can think of a lot of applications which will be of really great value for the understanding of the atmospheric structure. So let me just conclude here. So we saw this really highly dynamical and structured chromosphere, which has the shock waves and cool regions in between, and also this magnetic field is evolving really fast. And we saw that this non-equilibrium modeling is mandatory for the chromosphere, at least for hydrogen ionization, and also for the number densities of carbon monoxide, if you're interested in that. But CO is not important for the structuring itself. New diagnostics for checking the models are coming soon, like ALMA, which will be really nice. And of course more work is needed to add more non-equilibrium effects and to improve the realism of these simulations. And this in particular, one of the next steps will be efficient non-LTE radiative transfer for the solar atmosphere. Thank you very much.
Thank you. I guess you could rename the code 6 bolt now, since
yeah, but it's not important enough, so let's keep it.
Questions? Paul.
When you have non-equilibrium rate equations, which are stiff, you have additional numerical issues. What was your scheme for?
Can you repeat the question?
Yeah, so the question was, this rate equation system is usually stiff because you have got a range of different time scales for different reactions. And so what was the numerical treatment for that? So what you did is then for the hydrodynamical time step, which is usually of the order of 0.1 to 0.2 seconds or so, you just kept the thermal structure of the atmosphere constant, so means the temperature doesn't change over this time, which is fair enough, I think. And then the rate equations were solved separately with an implicit scheme to really account for short time scales.
At some point, of course, it will be important to include magnetic fields, because only in that case one can really expect a real spatial bifurcation into, at least according to traditional views, into a CO-dominated part and a CO-less dominated part. Would you actually still think that this is true, or do you actually now think that the magnetic field will not make such a big difference, even though you haven't really tried it yet?
How would you make this
you would have a cellular structure, of course, which is imposed by the magnetic field, which makes strong lateral mixing less strong.
Yeah, we did some preliminary simulations with MHD and molecules, and I didn't see a application there either. So it might depend on field strength actually.
And the observations are well reproduced, even with the current models.
Yeah, I think that's, I don't expect it application.
You have a way to produce from your simulation a theoretical picture. But if you get an ALMA image of 2012, how do you go backward?
Yeah, so of course the first problem is to really analyze these ALMA data.
Right.
And so what you will see then, or will not see, is how well these observations will be reproduced. Are these temperature amplitudes, for example, are they the same as in what's coming out of the model? Or do we,
So it's not a direct image comparison, but rather than analyzing velocity structures.
Oh yes, that's one nice thing with ALMA. It will also give you some velocity information, and hopefully even information on the magnetic field directly. So those will be really valuable contributions. So there are a lot of different things you can actually compare.
One last question.
Is there any role of thermal instability here? It used to be much spoken of in chronospheric discussions.
You mean if there's some thermal instability that is of importance for atmospheres that we found here?
Chromosphere, yeah.
For the chromosphere, thermal instability. So thermal instability means, for example, if you have some that runaway process that...
it's an instability in the sense that if you make it a little hotter, it radiates less, so it gets hotter yet, and then some other process will control it.
So actually the whole process would work, actually. So we made some experiments with this carbon monoxide cooling. And if you don't disturb it, then you really get this runaway process. So there is some instability. Just it doesn't get the chance to work, really.
Well, it works if the area will stop it. We'll balance it, but it's part of the dynamics, I would think.
So it's in there, but it's just insignificant.
Okay, thank you. I think we should continue with the next talk. Maybe it will come up there. So. You need to know what the slope is. Heating transfer, which is constant, and the cooling, which goes like T to the power of theta.
Yeah.
Then you want theta to be less than 1 for instability. Yeah. I need to look that out. You don't know. Okay, so the next talk has already been partly introduced by the previous speaker. This is Jorrit Lennart from Utrecht University, who will be talking about time-dependent hydrogen ionization in the solar atmosphere.
Thank you. Well, thanks, Ben, for
soon doing some introduction work for me. So I will talk about time-dependent hydrogen ionization in the solar chromosphere mostly, because the assumption of instantaneous statistical equilibrium does not hold there. So I will first explain why this is. I will explain something about the method, how we actually implemented this in an MHD code, show you the results, and there's still quite a lot of work to be done, so I will spend some time on that as well. So why would you want to do hydrogen? Well, it's the dominant component of the solar gas. It makes up 90% of the nuclei. So you better have hydrogen treated correctly in your simulation. Well, it is not an instantaneous statistical equilibrium in the chromosphere, and this hydrogen ionization is very important for the equation of state of the gas, because most of the internal energy of the gas is actually stored in hydrogen atoms in some form or another, or in ionization energy by ionizing hydrogen. And hydrogen lines are very interesting diagnostics for the solar chromosphere, especially the H-alpha line. Looks very interesting, like this H-alpha line core movie taken with the Swedish solar telescope. You see lots of structure, totally magnetically dominated, lots of dynamics, and this is all hydrogen light. So hydrogen is very interesting. You want to have it? I don't know. I would say that this is about 5 micrometers, but I'm not sure. So why do you want to do time-dependent hydrogen ionization? The ionization recombination timescale in the chromosphere is pretty long. In shock waves it's about 10 to 100 seconds, but in the cool intershock areas it might be as much as 10 to the 5th seconds. However, the atmosphere, the shock waves that propagate through the chromosphere changes on timescales of about 100 seconds. So basically hydrogen ionization will not follow the temperature and density changes. To illustrate this, I can show you the two-level atom. Assume we have a two-level atom, and we have it in some state. It is in equilibrium. Then we perturb the state, we change the density or the temperature, and the rates, the transition rates between the levels will change, and the populations itself will adapt to the new circumstances. Well, these are the equations. You get some nice mathematical solution. But in a graph, what you can see is we have something here. We suddenly change the atmosphere, and the level population will take a while until it gets to its equilibrium solution. This time scale is given by the rates, and if this time scale is really long, compared to dynamical changes in the atmosphere, you have this effect. If you want to do the detailed radiative transfer of hydrogen in a simulation, you need the radiation field in each transition at each frequency. However, doing this in detail is computationally very expensive and maybe not even possible in 3D simulations. In 1D it can be done, as the simulations by Carlson and Stein have shown. However, you need this radiation field. 3D this is a hard problem because you need linear rate equations. Fortunately, Asmus Solom, a master student in Oslo, showed that you can actually use fixed radiative rates. What you do is basically in each transition you specify the radiation field. He checked this in detailed 1D simulations, and it turns out that if you specify the radiation field, you do not compute it, but you just say it has to be something, you get out almost the exact solution. Of course, you have to tweak the radiation field to get the correct solution, but you can do that using these 1D simulations. So how does it look? If we have one column of the simulation, this is height, so here is the convection zone, this is up into the corona. In the convection zone you set the radiation temperature equal to the local gas temperature, but above a certain height you basically set it constant within a transition, and the solid line is here the local temperature. So you see it's totally different from the local gas temperature. Now the rate coefficients that enter in the rate equations are now totally local. We have the collision rate, which depends only on local temperature, electron density, and now you have the radiative rate, which depends on the radiative temperature, which I have set. I know this one, and I have the electron density there for bound-free transitions. So what you now can do is, in tandem with the hydrodynamics, solve the evolution equations for the hydrogen population. So this is basically an attraction equation, and here you have sources and sinks. which describe the transitions between the different levels in your hydrogen atom. We did this in the cobalt code. We treated hydrogen as a minority species, so there is no effect on the temperature of the gas. So here we have a 3D model that you see the temperature with the shock waves running through the simulated chromosphere. And here you have the ionization degree. You can still see it varies in time, but in LTE, in the cool parts, you would have hydrogen totally neutral, and in the shocks it will be totally ionized. And here the yellow-red coding indicates about 1% of ionization. So you basically do not see the shock wave pattern anymore in ionization. But as a next step, we wanted to include the backcoupling to the equation of state. 1D models have shown, and this is really important, so we wanted to have this in multidimensional simulations. What I wanted, hydrogen ionization affects the temperature, the electron density, and the gas pressure. So now you have to do something extra. You not only solve the rate equations, but in tandem with that, you solve energy conservation. So what you basically do is you specify, or you compute how the internal energy of the gas is distributed between the different contributions that you can have: ionization energy, excitation energy, hydrogen atom for molecules. Then you have to have charge conservation, particle conservation, and we include chemical equilibrium between atomic and molecular hydrogen. This is important for the cool areas of the gas because this works as a kind of a thermostat that keeps the temperature from dropping too low. If you work out all the equations, it turns out that you get 8 coupled nonlinear equations per grid cell, which you solve implicitly twice per hydrodynamical time step. You have to do it twice, has to do with the particular form of the hydro solver that we use in the code. So we performed a simulation. We implemented this algorithm in the also-diameter code. We did a 2D simulation, 16 megameters in the horizontal direction, 11 in the vertical direction, from the convection zone up into the corona. The radiation is treated with scattering, so it's not LTE, it is with scattering, but the tables that you use to compute the local Planck source function, the opacity, and the scattering probability are still using LTE ionization. So I want to point out that this is still a big discrepancy, and we still have to work out how to make this consistent with the non-equilibrium ionization. The equation of state tables, so tables that give you the pressure and the temperature as a function of the density and the internal energy, are actually not used. Using the non-equilibrium algorithm, you explicitly calculate the temperature and the pressure. Here we have a snapshot from the simulation. We have lots and lots of quantities, but let's start here. This is the temperature. So here we have the convection zone. I cut out the lower part of the simulation because it doesn't show that much interesting things. We have magnetic fields included. Here 2 magnetic field concentrations in the photosphere that fan out up into the corona. The corona is red here, about 1 million Kelvin. And in between the photosphere and the corona, you have the dynamic chromosphere with lots of shock waves. These areas here in between are actually not field-free. You can see here, this is the magnetic field map, that there is actually field here. You don't even see the difference between the magnetic elements and the internetwork in the magnetic field map. Here we have the hydrogen ionization degree corresponding to this temperature distribution, and has been shown before in the cobalt models. You do not see the presence of the shock waves anymore. It's basically a smooth transition from the ionization minimum at around 500 kilometers above the photosphere, and then it increases smoothly up into the corona. This is a dynamical simulation, so I show you a movie. I think it's about half an hour. No, it's 25 minutes of solar time. So you see the shock waves running up into the chromosphere. And here you see the corresponding ionization degree. So when you start this up in start of the calculation, we start in LTE. So you have some areas with low ionization degree. If it restarts there. But really soon this disappears and you are basically left with the smooth ionization degree that you have.
Now we compare this with an LTE simulation. So we took exactly the same simulation setup. We started from the same snapshot in LTE, but the left-hand panels were using the LTE ionization, the LTE equation of state, and the right-hand panels we show the time-dependent ionization. These are horizontal cuts through the atmosphere. So this is the horizontal distance. This is time, and we have it for different heights. 1 megameter, 1.5 megameters, and 2 megameters above tau equals 1. And at 1 megameter there's not much difference. What you might observe is that in the time-dependent case, the cool areas are a bit larger in general. But if you go to larger heights, the differences become very profound. In the time-dependent case, the shock temperatures go up. They can be as high as 12,000 Kelvin here, whereas in the LTE case they're only 6,000-7,000 Kelvin. And in the cool intershock areas, the black areas here in between the shocks, here the temperature can be as low as 2,000 Kelvin, and it actually is quite often only 2,000 Kelvin. Whereas in the LTE case, it stays at 4,000 to 5,000 Kelvin. So the temperature fluctuations really increase. And in case you wondered what this red stuff is, this is the corona, which is sometimes dipping down through the slice that you made. So it appears and reappears. As a side effect of this computing the time-dependent ionization, you also get the hydrogen populations for the excited levels. And in particular, you get the hydrogen populations for the H-alpha lower level, the n equals 2 line. And this is important for interpreting observations. So one particular observation is that of dynamic fibrils. This is a dynamic fibril. It's a black thing here which starts to extends further, and then falls back down again, as seen in the H-alpha line core. If you now follow the top of the fibrils in time, so here we have horizontal position, this is time again, they follow parabolic paths. I have shown two examples here from a paper by Tuponcello et al. And in this paper they compared this with numerical simulations using the same setup as I did. How much? 4 minutes. Same setup as I did, only using LTE ionization. And they showed a time evolution of a shock, or of a column in the simulation. And what you see is that shocks run up and basically have the same parabolic shape. They did some more extensive analysis and they concluded that the dynamic fibrils that you can see in H-alpha are actually similar to the magnetoacoustic shocks that run up in the chromosphere in the simulation. However, they did not do radiative transfer modeling, so they based their conclusion only on similarities in behavior, but not in synthetic spectrum. Now we go back to my simulation again. So dynamic fibrils sit here, where the straight above the magnetic concentration in the photosphere. Shocks run up along the magnetic field lines and fall down again. And if you take a vertical cut here and you follow the time evolution again, you see this nice parabolic shapes, whereas in the internetwork here in the middle, you see a much more random pattern. Here we have the n equals 2 hydrogen level population corresponding to this temperature, and the n equals 2 population is proportional to the H-alpha opacity. So what you see is that the top of the shock front actually has increased H-alpha opacity here, and if you then compute the column density, which is a tracer of the optical depth in the H-alpha line, what you can see is that in your dynamic fibrils, the column density is always much higher than at equal height in the internetwork chromosphere. So in between here, where you don't have dynamic fibrils. So this would explain that you can actually see dynamic fibrils on top of some kind of a bright background, because the surrounding atmosphere is actually transparent for H-alpha. Still, we have to confirm this with detailed calculations. This is something we want to do in the future. So, I reached my conclusions. So for the first time, we included this time-dependent hydrogen ionization in multidimensional simulations of the solar atmosphere. The temperature fluctuations in your chromosphere increase compared to LTE ionization. The ionization itself is rather constant over time and space, and the H-alpha opacity is highest above magnetic elements, so this is a possible explanation for the dynamic fibrils. What do we want to do in the future? We want to perform 3D simulations. Adding actually 8 extra variables in your code makes it really, really slow, so 3D simulations are kind of tricky, but I think we can do that in the future. We want to develop better methods for the radiative transfer. Right now the radiative transfer is still using LTE tables, and this is not consistent, so we have to think of a method to improve it. And then we want to compute synthetic H-alpha spectra for comparison with observations. So that's it. Thank you.
Question?
This is, of course, extremely nice work, but there's still something which is fundamentally different if you compare to the observations. If you take one of the first slides, it may be taking too long to find it, but we all know it. When we look at the chromosphere in H-alpha or calcium, we see these relatively long filaments. And in the movie you showed, those filaments are quite dynamic. Yeah, that's a good one. And also the movie, yeah. Look, you have lots of flows up and down the filaments. And modeling that requires simply a scale big enough to cover the endpoints of the filaments.
Sure, you cannot simulate all of this, or at least not yet, but these dynamic fibrils, if I am correct, I'm not an observer, are probably these way smaller features that you can, for example, see here. So simulating this stuff, or even that thing, is way out of the question right now.
Aren't those spicules down there? What they
I do not want to get into the controversy about the names, but I don't know.
Come on.
You use now 2 codes for similar things, and the latter code is casting code in each of the corona, but there is some sort of common area both one and the other code can do. Do they agree or disagree on sort of if you put in the same assumptions or simplify both to have common denominator?
Well, I have not done a real comparison, but in a sense, if they would agree, I would be very surprised, because in the couplescope we did not implement this back coupling, so the temperature structure will be quite different. So it might be interesting to compare, but if they are the same, I probably make some error.
You cannot switch it off in the casting code.
Yeah, you can run it.
I look at these similarly.
Should be possible, yes. Why not?
So, this time
Yes, in fact, my remark I want to make after the previous talk, but since we are still in the chromosphere context, I think it's still appropriate. Maybe a little bit cross-disciplinary. I would like to emphasize again that people in the cosmology community, in the star formation community, especially those who sit in decision-making bodies, that ALMA will be very interesting instrument, also for solar physics. I understand that people see that as very interesting for cosmology, say, observing such marvelous things like a similar cell, which is looking at molecules and star forming regions. I understand this is all very interesting, but ALMA was initially received as also a solar instrument. Now budgetary turmoils may make questions come up. What can we say? But still, I would like to emphasize that it's interesting for solar physics to solve some of the pressing questions about the structures in the chromosphere. Thank you.
Okay. Thanks. I think we the microphone.
That would be very interesting. Sorry?
It has a clip. Yeah, I can turn it off. And don't come to me with mistakes because of feedback. Can you? Oh. Okay, so now we move away from the sun and we go to smaller star-like objects. As Christiane Helling will talk about the challenge of substellar cloud formation modeling.
Thank you, Fred, and thank you for inviting me to give this talk on something completely different, it might appear at first, but since I'm giving the talk, I'm of course picking those aspects which I think are the most exciting. And, oh no, wait a second. And talking about cloud formation, everybody of you has, of course, a picture of clouds in mind, like these beautiful cloud layers in Scotland, for instance. If we go out in our own solar system, we certainly know that our everyday life is kind of that Jupiter has clouds, that Saturn has clouds, that Venus has clouds. But the question is now, nice for our own solar system, but it hasn't been that obvious for the rest of the world, so to say, for the rest of the universe, that other planets should also have clouds. And therefore I think I dare, as a theoretician, to show you some of the observational results being just released on AstroPH, and you may notice the short date when it appeared. Anyway, the point is, here the first Spitzer observations have been published, sorry. And the basic of it is actually the same data set. This is an observation from a secondary eclipse, and I'm just talking you quickly through it. The authors have averaged 280 spectra and have plotted it. Then they averaged the two spectra of the two observations. But then the important point is this bin spectra. Now you can argue if it is wise to do that, but anyway, what led the authors to the exciting conclusion in my eyes is actually that they have kind of a data point up here, which is in a dust absorption wavelength spin, and the conclusion is then, of course, consequently, there must be some high-altitude silicate clouds. So the other method comes to the same conclusion, which is for a theoretician a little bit more straightforward, because they simply compare to some kind of a semi-classic model atmosphere, and you see that the observations lay way on top of the fluxes derived from the model atmosphere. So now, you certainly have realized that these are not absorption features, that these are emission features, which is a little bit uncomfortable, but on the other hand side, it's clear that these planets are strongly irradiated, and if you look at our own Earth, we also have a temperature inversion in the atmosphere. And in order to get onto the topic a little bit further, I have picked another recent observation in order to at least give you an idea on this habitability issue. Because the race is now on for the most Earth-like planet, right? There is the first one coming up by microlensing. It turned out it is far too far away from its host star, so it's kind of a rocky Neptunian. But then we have the recent observation by the Udry et al. And they come up with a 5.03 Earth mass planet. Of course, you have to multiply it by 1/sin I, right? So. But the nice thing is it orbits its host star at 0.073 astronomical units, which leads the authors to the conclusion that the planet resides at the inner edge of the habitable zone, which in normal person's words means that they do expect liquid water on the top of this planet to be possible. The problem with this whole habitability argument is, of course, that this is it's a thermal stability argument, and second, it hasn't taken into account the whole system, including the atmosphere, what I'm obviously up to, and the atmosphere certainly will play a very important role in judging if this planet is habitable or not. So, and now there I am, where I wanted to be. The planet scientist's wisdom for us today is we have indications that there are high altitude silicate clouds, and of course the atmosphere, the understanding of the atmosphere is essential in order to decide if this object is habitable or not. Now I have dared to group the present day's tribes in brown dwarf and planetary atmosphere modeling into 4 categories. I certainly do injustice to some of my colleagues. I apologize for that, but I think these are the main streams right now. There is the classical approach from gas phase radiative equilibrium. This is one-day hydrostatic chemical equilibrium in the gas phase, and if needed, then some cloud parametrization has been incorporated. It is clear that this is a very quick approach, a very fast approach, and it's very, very accurate in radiative transfer calculation because people incorporate millions of lines. The third box I'm opening here is the 3D hydrodynamics, and I'm now talking about planetary atmosphere, so sorry if I'm not listing your particular name on here. And since I'm going towards the cloud physics, also obeying the fact that 3D hydrodynamics takes so much time, that a certain approximation in the cloud physics is needed as well. Okay, then another very exciting tribe is the photochemistry of exospheres, and this is again kind of fostered by the HST observations of the planets, because people are suddenly in the need to come up with some kind of crazy non-equilibrium number densities for instance, natrium. And then the last one, which I like definitely the most, is the chemistry and the physics of the cloud formation itself. And why I'm raising is of course because I have been heavily involved in it. And by now we have indeed succeeded to couple the whole model approach to a one-day hydrostatic simulation, which again has the classical approach of chemical equilibrium in the gas phase. But then the strength of it is, of course, that we are able to treat the actual formation. It means the nucleation out of the gas phase, growth and evaporation, and the drift process, meaning the relative motion between the gas and the dust formation, between the gas and the dust of composite cloud grains. So we are not looking at homogeneously composed grains, for instance, made of iron or whatsoever, but they are really, really dirty grains. The aim of let me go back one step. You certainly realize that each of these tribes has its strengths, but also its weaknesses. And this is, of course, justified, because in the end, the idea of all these modeling approaches is to predict and explain observational quantities. And since we are physicists, we want to understand the physics and chemistry of that what we are actually going to see, or what our observers colleagues do see. So, the challenge of the present day's stellar model atmosphere is actually to come up to include a proper description of cloud formation, and this is something relatively new in the atmospheric environment. By now, dust formation and cloud formation has been treated in AGB stars very successfully, but brown dwarfs and planets really call for new physics and new chemistry in these even cooler atmospheres. So, and now, I think I would like to give you a little bit a picture in your mind what I'm actually talking about. I have been racing through a kind of introduction, and this is, here I try to summarize in a sketch the basic physics and chemistry going on. It may look a bit crowded, it may look a bit simplified. Anyway, in this direction, high temperature and high densities go. That means here we are kind of inside the whatever substellar atmosphere, and this then obviously points outwards. You certainly realize there are different scales and different kind of processes involved. On this hand side I have collected chemistry, on this hand side I have collected kind of the physics, and you see there is somehow large scale things going on, and there are small scale things going on. I'm now very, not very precise, but anyway, we know that by now we know quite a lot about these atmospheres. First thing, they are largely convective. Second thing, they form dust. So, and these arrows simply indicate that there is some large-scale convection going on. But I'm jumping to the chemistry side. At some temperature and some pressure, the atmosphere is gaseous, right? There are there are quite some molecules around from which at some certain temperatures, when the gas is highly supersaturated, dust grains, nuclei form out of the gas phase. The moment these nuclei form, they provide the first surface out of the gas phase. And the moment these first nuclei form, a lot of other solids are already thermally stable. That means the moment the first surface forms, they start to grow onto the surface, because surface reactions are much easier than the actual gas phase solid transition, or whatever gas phase liquid transition. So this brings me to the point that I'm dealing here with a highly chemically complex system, namely with a carbon-rich atmosphere. There is not such thing like a homogeneous dust grain. Each dust grain forming in a brown dwarf or in a planet will be heterogeneous. It will be dirty. Okay. Once these dust grains have grown to a considerable size, not even the moment they have been formed, they start to gravitationally settle, they start to rain into the atmosphere, and of course change their composition and their size while they are falling down. Okay, if you take this idea a little bit further, then you realize that none of the hydrostatic atmospheres should have dust at all, because it forms, falls down, it's gone. So we need a kind of a counteracting mechanism, and then of course convection comes into play, fortunately. So we have a very nice physics providing a mechanism to element replenishment those atmospheric layers where the dust has formed. Let me just make two additional points to this very general picture. One thing is, of course it depends on which object one is actually treating. It depends on if you are looking on brown dwarfs or giant gas planets, or if you're looking at the terrestrial planets. The fundamental difference for the dust formation process is that on the terrestrial planets you have a crust where you can kind of mix off, where by updrafts seed particles moved into the atmosphere. So you kind of circumvent the nucleation problem, which one has to treat in looking at brown dwarfs and gas giant planets. The other point is the convection part. It appears that we have here a very efficient mechanism to drive a quite turbulent fluid field, which in some sense then will also interact with the chemistry. Okay, answering the question about the equations we are treating, this is actually kind of the amount of equation, or the characteristics of the equations one has to treat. There are the hydrodynamic equations. I won't go into details into that, because there are more experts on that here than I am. But then there is the dust formation coming into play. Of course, I have plugged into it. I have written out here now our dust model. I will come back to this in a second. And in addition to hydrodynamics, the dust formation equations one has to solve for the element conservation. And this becomes at some point pretty painful, because one has to treat as many equations as elements are involved in the dust formation process. And if you then go back and see, in the models I'm showing you in the following, I'm treating my source in the energy equation as a relaxation ansatz, and the dust formation couples via the opacity in here. And this brings us down brings us back to the aspect of very stiff equations, because dust formation is a very quick process. That means suddenly this equation becomes a very, very gets a very, very big source term.
Christian?
Yep.
What are the, this is capital M and FR.
Okay, now you got me. What I did, this is actually written down in dimensionless form. So this is the Mach number, this is the photon number, this is the radiation number. These are characteristic numbers. So all the scales are kind of, comprised in there, and what is left is actually the functional dependence. Yeah, sorry for that.
That's fine.
Okay, so as promised, some more equations on the dust part, because this is what I have been growing up with. The basic idea of coming up with a closed model for the dust formation goes back to Geil and Wedemeyer in the late 80s, and it makes use of the definition of so-called dust moments. It's a definition of moments, and this is simply an integral over the grain size distribution weighted by some power of the grain volume. And the basic idea is, of course, that nobody of us really likes to solve equations for the grain size distribution function, which brings one back to the Boltzmann equation. So this is getting to be pretty painful. Therefore, if one carries out the whole procedure, one can derive some some dust moment equations, and if you see, they have exactly the same structure like the hydrodynamic equations. So up to here it's pretty classic, and then at some point we had to think, how to treat the formation of heterogeneous particles, and this brought us to the idea that one can derive it, it's not just something that falls from the sky, that one gets a similar conservation equation for the actual solid volumes, and you see, and then one has to write down them for each of the solids involved. I don't want to go into too much detail. You can ask me afterwards about the backgrounds, but let me just mention one more thing. I have highlighted here, at least I should tell you what these source terms are, right? Sorry. The source terms of these equations are the nucleation rate. J is the nucleation rate, that means the number of dust particles formed out of the gas phase, and then this describes the growth. So this means it's the growth speed. And if you go down to this line, you see that there is this bracket. And the thing you need to recognize is that here the supersaturation ratio goes in. That means no growth will happen if the supersaturation equals 1. That means every model assuming supersaturation equals 1 is an equilibrium model, and there shouldn't happen anything. Okay. And there are other non-equilibrium processes which goes a little bit too far right now. Okay, let me make another point which brings me to the difference between the large-scale simulations and the small-scale simulations. If we now have a look at some space-time variable and treat it in the Reynolds decomposition, that means one splits the macroscopic or resolved part from the microscopic and fluctuating part, goes, of course, in my case, to the dust equations, never mind. Then one comes up with, again, with a separation of scales. There is a term which just relates to the large scales, and then there is a mixed term. And this I have written out here. And this mixed term is again a mixed term, and then it couples the small scales. And now the question is, of course, since we are dealing with a highly reactive system, are we allowed, can we physically justify to kind of neglect everything what is going on the small scales? And this is one of the things I would like to address in the following. Okay, I'm speeding up right now. The idea here is now to investigate the interaction between turbulent fluctuations and dust formation. So is there any effect, or can we simply neglect small scales? The philosophy behind was that there is convection going on, and the convection kind of can create superimposing waves. That means I'm representing very simply right now turbulence as some kind of wave motions. And the basics of this whole thing is the solution of the high dynamic equations I have shown you with the dust equation I have shown you as well. This is a one-dimensional simulation because I'm interested in figuring out what physics and chemistry is going on, right? So this is the initial condition. I have two expansion waves moving towards each other, and then I'm putting myself here at the point of maximum interaction and look what happens. And this is what happens. This is the time evolution of density, pressure, gas, velocity, then dust complexes, the nucleation rate, and mean particle size. Let's go to the temperature. Temperature drops to a certain point. This is the point of maximum superposition, and then dust starts to form. And now runaway process happens, because the moment dust forms, it starts to grow. And this means the opacity of the whole system increases. So that means the growth, the cooling becomes even more efficient and drops at some point very rapidly towards a radiative equilibrium value. So that means there is a strong correlation between small-scale fluctuations and dust formation, because turbulence can indeed initiate dust formation. Due to its radiative cooling, it causes the area of dust formation to implode. You see that the density increases quite a bit, and it even feeds back into the turbulent velocity field. This is an temporal increase of the velocity by 10%. The idea is, of course, can we make use of this result, and how much sense does it make in a more dimensional, in a more complicated simulation? Here I'm showing you the results of a two-dimensional simulation where the initial situation is dust free. I'm driving turbulence on the left, right hand side, and on the bottom, and let's to simulation 1. What you see is how much dust forms actually. And the point I want to make is that dust indeed forms as small on small scales. You see, if you have a look, for instance, here and there, then you see this was a very small, very refined cell, and then it really increases. And we had this, and there is a transition from adiabatic behavior to the isothermic behavior due to the strong radiative cooling. And then there is also the tendency of forming larger and larger structures, because vortices appear and just grab the dust and kind of collect it into larger structures. Okay.
Sorry, what's the scale of these boxes?
Well, it's in a sense it's scale free, yes. But it's of course again non-dimensional, and this is what is it? It's half a test volume. It's 500 meters. So now I would like to jump. Sorry for bothering you again with the equation, but I think since most of us are theoreticians, and the one who has asked for the equation fall asleep, I'm very sorry for that. Another point is one point of the business is to study the small scale processes. And another point of the business is, of course, to come up with a proper simulation, or with a proper dust model for the hydrostatic one-day simulations. And this is what we actually did. This is the whole equation, including the drift process. And if we are now aiming at a hydrostatic representation, the time dependence goes away, and the gas velocity is also zero. Okay. And at the remaining time of the talk, I'm going to talk now about the real large scale regime, namely about the dust stratification in Brown-Dwarf atmospheres. And I have to do it pretty quickly. This is a pretty busy plot, but it doesn't matter because I can talk you through that. So this is the upper plot. Shows what we have to, or what we assumed in this model. We don't have to, but we did. This is the temperature pressure structure and the time scale of upmixing of material, and this is the dust complex, which is a result of the whole simulation. Okay. All quantities are plotted as function as pressure, and we could the physics is actually can be divided in 5 different slots. The uppermost atmosphere is dust-free and gas-depleted. The reason for that is that here the nucleation rate is very small, and any particle forming up there will move inwards. So that means what remains is a highly depleted gas phase. Going further inward, nucleation rate increases. That means most of the particles are formed up here, and if you see, it relates. This is the mean particle size relates with a very small particle size. Going further inward, nucleation rate decreases, supersaturation ratio decreases. That means every particle being in here has been reined in from the upper atmosphere. Okay, and then the mean particle size increases quite rapidly, which as does the drift velocity, until it reaches a region where, this is region 3, where it's drift dominated. This means the particle cannot grow any more further, because the growth time scale equals the gravitational settling time scale. And at some point it reaches atmospheric layers where it simply evaporates. Therefore the mean particle size becomes zero. Decreases and becomes zero. Besides these 5 regions, which are really governed by basic physics processes, is the bottom line that the whole structure is determined by a phase non-equilibrium process and the non-locality of the dust formation. So, and since we have to deal at some point with observations, I'm not driving you towards a first idea on how these cloud structures should look, how the spectra of such a cloud structure should look like. And I'm just showing you here the grain size distribution in such a substellar atmosphere. And you see here, this is the number of dust particles per grain size volume. And I'm just stepping from outside inward. It means the numbers subsequently count through some atmospheric layers. You obviously don't have 14 atmospheric layers, there are 200 whatever. But I just grabbed some illustrative examples. So that means here again in the upper atmosphere, the grain size distribution is quite narrow. That means here the nucleation goes on, but then it broadens. You see it considerably broadens. That means particles grow, and constant and still nucleation is going on. It means more dust is formed. If we go on, it reaches a saturation ratio. That means nucleation has stopped. And then at some point it gives, there is a big jump from kind of moderate sizes to huge sizes. And this happens because some particle can simply grow to huge sizes. And then you see there is a motion, a movement back into grain size space, because then of course particles evaporate and then they are gone at some point. The nice thing is now that we can make predictions on the chemical composition of our dust grains. This is the material composition, and I have plotted it in a kind of strange way, because this is the temperature, these are low temperatures. It means here we are up in the atmosphere, here it is hot, we are low in the atmosphere. It's again a busy plot. The message you should take away is that in the upper atmosphere the dust is mainly composed of silicates and silicon and SiO2, and that of course due to the temperature changes in the atmosphere the chemical composition changes considerably. And in the inner atmosphere, there we have large grains which are mainly composed of iron and corundum. Okay, how does it look like? I have a nice colleague sitting right now in Edinburgh who does simply these relatively quick computations. This is now a pure, a computation for a pure dust layer. We haven't taken into account any radiative transfer process on top of it, and it's nice to see that actually our most important species show up. This peak should be due to SiO2 and Mg2SiO3, and this is due to MgSiO3 and SiO2. So this seems to be relatively logical.
You have it on the slide.
Okay, cool. Then I can spend a little bit more time. Okay, I have shown you now results which directly relate to the work I have been doing, but I think it's also nice in such a talk to put it into a larger frame, and in particular I'm aiming at a comparison workshop we have been doing last autumn in Leiden. For that I just I'm showing you this plot which has been done actually by Matthias Dehn during his PhD thesis, and this plot compares effective temperatures with plots effective temperatures as function of the J minus K colors, and these are results from one-dimensional static model atmospheres for LLT dwarfs, which all incorporate different ways of treating the dust clouds, or the dust, representing the dust clouds. This plot is relatively old, it can by now be updated, but anyway I think it nicely shows the general trend. These crosses are representing limiting cases. These are the so-called T-dwarfs. They don't have any clouds in the atmosphere, everything has been consumed and has been moved below the tau equal 1 level, and these are the so-called T-dwarfs. They have lots of clouds in the atmosphere. Okay, these are two representations, and then there is another model approach where people just tune the grain size in order to represent the transition from the L-dwarf regime into the T-dwarf regime, because the idea is that what has been an L-dwarf, or what presently is a L-dwarf, thus develops into being a T-dwarf due to simple cooling of the object. So that means every model should actually kind of be able, or every code should be able to represent this turn back from the L-dwarf regime into the T-dwarf regime. And you see, and these are our results, none of them who kind of do try to sensibly model the dust formation part do. And now the problem is, of course, what are the reasons for that? And this is why we set out to have had a workshop at the Lawrence Center in Leiden last autumn, where we invited those people seriously interested in cloud formation modeling in brown-dwarf atmospheres and in gas giant atmospheres. And I'm showing you now here two recital quantities. Here I'm simply comparing the amount of dust present in the atmosphere, and here the mean grain sizes. And the exercise which has been done here is each of us has been given 3 atmospheric structures, and each of us was supposed to run the dust cloud model on top of it. So that means the only uncertainty here is actually, or the only difference is, the difference here is the dust cloud model. And you see how different the results can be. The plots have been done in such a way, in a kind of historical way. Takashi Tsuji was the first one who actually suggested that there should be something going on with dust formation in brown dwarfs. So he's actually the guy in the field. And you see then this Magmali, then the Ara et al., they didn't deliver yet, and us. And I think you see there are common features and there are very vastly different features. One common thing is definitely that all the cloud models, they stop at the inner, they have the same inner boundary. And the reason for that is, of course, it's linked to thermal stability. So if the solids are not anymore thermally stable, they shouldn't be present. So the differences are, for instance, the extension of the dust clouds, and then here Marley and Ackermann even have a detached cloud sitting up here, and the reason for that is that they form, that they treat water formation up there. Another thing is the mean grain size, and this is actually an important quantity going into the radiative transfer treatment, right? Then again, one approach is to simply assume a very small grain size so that the grains are just hovering in the atmosphere. Ackermann and Marley, they can calculate for each of the dust species different grain sizes, and then us, we have a kind of a continuous distribution of the grain sizes. So this doesn't look too different, but again, the location of the dust clouds are vastly different. And we have been working on the reasons for that, and we are just on the way to get everything together and to publish it and show it to the community. So I'm not bothering you any longer with equations and things. I'm just I was thinking what future challenges should be, and I came up with four which I think are the most interesting. The first part is, of course, if we do cloud formation modeling wherever in an atmospheric environment, we have to accept that it is a non-equilibrium process. There is no way in treating a cloud formation as an equilibrium process. Then we have to tighten our strings to laboratory works, because all our equations are nice as they are, but in the moment we don't have any material quantities, we don't even need to start our simulations. And then, of course, there is the big issue which I started out with, of becoming more terrestrial without being actually terrestrial. With which I mean, of course, there are works going on in climate research and weather forecast and whatsoever on Earth. But these people can go out and test their model with real data. We just have a spectrum. So our way is way more painful than theirs. Well, it depends on the point of view. So what we need to do is we have to go for liquids. We have to kind of figure out how to treat snowflakes, actually. Nobody knows on Earth, so then photochemistry, and you already see it links back what I said in the beginning. There are, of course, works going on in these areas. Then there is the aspect of volcanoes and earthquakes, and life, of course, and volcanoes and earthquakes are very important for dust formation, or for the cloud formation part, and life also will somehow obviously feedback into the whole cloud chemistry. And another point, in case somebody wanted to ask, there is, of course, the issue of magnetic fields. And here I just had next door a nice paper coming up where people just suggest the search for planets actually by looking for their radio emissions, which I thought was a nice idea. I thank you for your attention.
Thanks, Christian. Questions?
You said just a moment ago that there was a jump from moderate to large sizes. You did that a bit quickly. Would you please repeat why that is?
Because on one hand side, I did real hydrodynamic simulations where I tried to look at the interaction between a representation for turbulence and the dust cloud formation, or the dust formation itself. The jump to the very large scales comes due to the fact that we felt the need, or that we felt that we had actually the tools in our hands to provide the atmosphere modelers community with a much more detailed cloud formation approach than what has been present previously. So that means we took our cloud model and kind of reduced it such that it could be applied in hydrostatic environments. And these are, of course, and these hydrostatic, these classical hydrostatic atmosphere simulations, they try to cover the whole atmosphere. In this sense, it's a difference between, 100 kilometers and 500 meters I had in the beginning. So that means one really has to take care in the entire atmosphere simulations, which are the basis for the spectrum calculation. One really has to take care for drift effects, for instance. So because the particle can... No, what was it what you wanted to ask?
Well, it's interesting what you say because it adds to what we didn't know, right?
Yes,
my question was actually about the particle size distribution. Because you said there also that it jumps from moderate sizes to large sizes.
Oh, okay.
I mean, you missed the Fox's approach, I think I understood.
Yeah, okay.
Up to a point. But you showed this diagram where suddenly the particle size distribution cut off at one point and there was a gap.
Yeah.
And then suddenly it was big stuff.
Yeah, I'm sorry I didn't. This one.
Yeah.
The point is with the particle size distribution, let me see. Here I'm going inward. Yeah. What happens? You have the whole dust complex moving inward, and as they move inward, they can continue to grow. But of course, those which are smaller, they will have evaporated earlier. But the others, they simply can move on for a little while, so they increase their size. That means there is not just one particle size at one certain height in the atmosphere. There's a whole range of particles. And if I then end up, or if I then, perchance, grab some height where the grain size distribution is really very small, I end up with one particle size actually along the cloud base, I think, cloud base it's called. And they just start then to fall through without any further growth.
Thank you.
I think that's what it is, yeah.
Yeah, sorry? I just want to answer Vince in one sense. In studies of raindrops in the Earth's atmosphere, it's found that a fully turbulent flow, just imposed, will sustain a bimodal distribution of drop sizes up there. Don't quite understand why, but that's
no, because the point is, I think, you're bringing up already existing particles and they continue to grow, and then other particles fall in from upward. So that means those brought up, which already exist, brought up from below, they will represent the large size end of the grain size.
But this is without any growth in there. They just somehow produce a bimodal distribution.
So it's effectively a two-stream instability, right? I mean, the small ones go up and the big ones go down, and just make it quickly and eat up the small ones, and that's it.
Yeah. I mean, if there are of course more issues. There's also the issue of coagulation, and then one really has to sit and calculate. I mean, this is what I also would have said. You have something coming up and something falling down, and since what comes up has already existed and has already a volume, and actually falls or comes through denser areas than that what's coming from the top. So they should be much larger than what's coming from the top, naively. But then again, there is the coagulation issue, so which neither of us has taken into account. It means, you see, the collision of already existing particles towards even larger, into an even larger regime, which hasn't been taken into account because it's just, in another science regime again.
You mentioned that a typical grain size in the deep atmosphere was about 100 micron. You mentioned in one of your graphs that...
I said that in that model they are about 100 micron.
So if they are significantly smaller, would you dare to put a number there? How much smaller? How much smaller are the particles in the higher layers?
Oh, I can tell you. In the lower layers they are 10 to the 2 micrometers, and in the higher layers they are 10 to the minus 2.
Okay, yes.
I mean, this is, again, there is not, you cannot just put one grain size at one layer. What I have been referring, I have been tremendously simplified. Tremendously simplified by saying it's 100 micrometer. There's 10 to the minus micrometer. There is a whole grain size distribution, right? This is not just one value. Okay.
Okay, it's time for a break. Thank you, Christian.
Can I make another?
And Axel has an announcement.
There is, she mentioned Gliese 581, and there is, by the way, on Friday after our meeting at 4 o'clock, there's an astrobiology talk here in the department on Uglise 581C. So, if you're interested, you can find it, of course, in the web. It's by René Lisseau.
Okay, so we have a break now until 10 past 4, half an hour.
This is the thing from this maybe, right?